The last type of calculation I want to look at is, will a precipitate form? If you have two aqueous solutions, things that are dissolved, and you mix them together, do you have enough ions in a high enough concentration that you actually do get a precipitate to form? Typically we look at this in terms of, I've got a container of, for example, let's say I have a container that contains sodium iodide, a sodium iodide solution, an aqueous sodium iodide. Sodium iodide is soluble. It will dissolve in pretty good quantities. So let's say that my sodium iodide concentration is 0.002 molarity. And let's say that I have 100 milliliters of it. If I dump this or combine this with a container that has 50 milliliters of lead-2 nitrate, lead-2 nitrate is also soluble. Anything with the nitrate ion is going to be soluble, even lead. So let's say my lead-2 nitrate concentration is 1.8 times 10 to the minus 4. It is a very low concentration of lead-2 nitrate. But again, these two aqueous solutions, if I dump them together, will I now have a precipitate? Will there be a solid forming in the bottom? So will anything form, will a precipitate form if I dump these two together? In order to answer this question, we need to analyze the two solutions and say, well, what would possibly form? In that case, let's look at the ions that are present. In my sodium iodide solution, I have sodium ions and iodide ions. I can calculate or determine the concentration of each of these ions from this starting molarity. In my lead-2 nitrate solution, I have lead plus 2 ions, and I'll get, notice, 2 nitrate ions for every 1 lead-2 nitrate that splits up. I only get 1 sodium and 1 iodide for every sodium iodide that splits up. I get 1 lead plus 2 and 2 nitrate ions for every lead-2 nitrate that splits up. But again, I can figure their molarities, their concentrations, based on the starting molarity of the ionic compound, of the salt. When I dump these two together, I then have these 4 ions floating around, and what would happen would be a double replacement reaction. Again, think of your Gen Chem 1. Sodium nitrate is going to be completely soluble, just as sodium iodide is in lead-2 nitrate, but lead ion and iodide ion have the possibility of forming the lead-2 iodide solid, insoluble solid. Back in Gen Chem 1, we wrote this as a double replacement reaction. We wrote sodium iodide plus lead-2 nitrate yields lead-2 iodide, which is a solid, and sodium nitrate, which is still aqueous. We then took it down to the ionic reaction and the net ionic reaction and all of that jazz. But for this chapter, for this semester, what we're concerned with is, will lead-2 iodide precipitate? Now in Gen Chem 1 we said of course it will because it's insoluble. But now we know in Gen Chem 2, well, it's actually slightly soluble. The question is, are these concentrations small enough that it will stay dissolved, or will a precipitate form? So this is the equilibrium reaction that I am concerned with. That's always the first thing, or the next thing, I guess, that I have to decide when I am given my initial solutions that are mixing. Now I can make this a little easier. I can write a question that's a little easier than this by just saying, hey, I've got lead ion concentration and iodide ion concentration of certain values, just straight off the bat. It's a little more difficult when I say I've got sodium iodide and lead-2 nitrate and I'm dumping them together. Then you have to figure out that it is the lead-2 iodide that I'm talking about as to whether or not it will precipitate. Notice that I wrote my equilibrium reaction starting with the solid and breaking up into the aqueous ions. I did that very specifically because I know the equilibrium constant for this reaction. The KSP for this reaction has that formula, and its numerical value is available on data tables as long as I'm at 25 degrees Celsius. And if I look up the KSP for lead-2 iodide, I see that it's 9.8 times 10 to the minus 9. Again, remember that our KSPs are unitless. So this is the equilibrium constant for this equilibrium reaction. I've got lead ions and iodide ions that I'm dumping in the solution, and the question is, will a precipitate form? In other words, will this equilibrium shift to the left, or are these concentrations small enough that it will stay dissolved? In other words, just like we learned back in the equilibrium chapter, I'm not necessarily at equilibrium when I dump my lead ions and iodide ions together, so I need to calculate a Q. The Q is like the equilibrium constant. It's going to be the concentration of lead ion and iodide ion squared, but it's as I dump them together, it is not necessarily at equilibrium. Now, you have to be a little careful here. If I had gone ahead and told you my lead ion concentration is X, my iodide ion concentration is Y, you'd simply plug those numbers in to calculate Q. It's a little more difficult here because I am dumping two solutions together. And when I dump two solutions together, I need to calculate the molarity using M1V1 equals M2V2. I'm essentially diluting my lead nitrate solution. I'm diluting my sodium iodide. So the concentration of my lead plus 2 ion, once I get it dumped together, is the molarity that I'm looking for. This is my M2. My V2 is the volume of everybody together. Now typically volumes aren't additive unless you have dilute solutions, and these are very dilute solutions. So my V2 is 150 milliliters, because once I dump these two beakers together, I'll have 150 milliliters. My M1 is the molarity of the lead ion that I dumped, my 1.8 times 10 to the minus 4. Again, be a little careful of your stoichiometry. If I'd been interested in the nitrate ion concentration, it would be 2 times 1.8 times 10 to the minus 4 because of the stoichiometry. And my V1 is the volume that that lead ion solution is. It's my 50 milliliters. And so the concentration of lead ion that goes into my Q calculation is 6.0 times 10 to the minus 5. Similarly, I'm going to do this kind of quickly. I'm going to need the concentration of my I minus. Again, M1V1 equals M2V2. .33 times 10 to the minus 3 molarity. I'm keeping an extra sig fig just because I am not finished with my calculation. I'm ready to go in and punch in for Q. It will be my lead ion concentration, the 6.0 times 10 to the minus 5, times my iodide concentration, 1.33 times 10 to the minus 3, squared. I do not double my I minus. I need the concentration of I minus, not twice it, but I do square it for my equilibrium constant, or in this case my reaction quotient, Q. So let me plug these values in and see what the value for my Q is. I end up with a Q of 1.07 times 10 to the minus 10. Again, I am keeping an extra sig fig. Recall what K was. I am comparing these two values. In this case, Q is less than K. Q is smaller than K. And we learned in our equilibrium chapter that if Q was too small, it needed to get bigger, which means our reaction would shift to the right. If Q was bigger than K, it needs to get smaller and our reaction shifts to the left. So in this case, Q is too small. We were looking at an equilibrium that would shift to the right. It won't actually shift to the right because I don't have any reactants. I don't have any solid, but it will not precipitate. It will not shift back to the left and form the precipitate. If I end up with a Q that is bigger than K, if the Q is too big, it needs to get smaller, which means a shift to the left, which means you would see the precipitate form. So in this case, my two solutions have small enough concentrations of iodide ion and lead ion that they will stay dissolved in the solution, and I will not see a precipitate form in the bottom of this.